Apologies in advance if I seem slightly distracted at certain points. Somehow, all these things have been very much on my mind, as is obviously the case for everybody. It's nice to have at least a few physical people here. I don't know how many people are watching this on the stream, but I'm sort of imagining that you're out there. I'm sorry I can't interact with you, but I'll do what I can. So I'm going to be talking about joint work. Let's just get this mentioned straight away with Jason Long. And it started with the following basic problem. Supposing you have a binary operation that let's say on a finite set X, and let's suppose it's injective in each variable separately. So people sometimes call it a quasi-group, because you have cancellation law or something like that. And let's suppose that if x, y, z is a random triple in x cubed, then the probability that x operation y operation z equals x operation y operation z is some number c. Then what can we say? That's a slightly vague question, but I'll make it more precise. So let me say something trivial first of all, or almost trivial, which is that if c equals 1, so this operation is just an associative. By the way, I'll call these triples associative triples. So the ones where you do have associativity, we'll call them the associative triples. So if every triple is associative, then the operation is associative, and it's an easy exercise just to sort of check that that really does give you a group. Yes, I said that but didn't write it, so perhaps I better. The next sort of, once you've done 1, the next natural thing to think about is what if c is very close to 1? So we sort of perturb the situation. Then, so if the operation is close to associative, then it turns out that what you've got is close to a group. Maybe I won't say exactly what that means, but, or then maybe I will say. So if c is close to 1, then you can find a group multiplication table, and you can sort of embed x squared isomorphically, or almost isomorphically, into here. So you can pick out some large percentage of the rows, some large percentage of the columns, and identify those with x. And then you'll find that the multiplication that you've got on x agrees 99.9% of the time, or some large percentage of the time, with the multiplication that you have in the group. So a small point to emphasize is the size of the group doesn't have to be exactly the size of x. So what you could do, for example, is take a group multiplication table, arbitrarily pick some large subset of the group, sort of 99% of the group, take the resulting multiplication table and then sort of mess with it a little bit to make it into a Latin square or a quasi-group. And then you'd have an example. And that's basically the only way of getting an example. And that's...
Is there a link between the size of the group that you invariant and the size of X?
Yes, that's what I'm saying. So the size of the group is almost exactly the same size as the size of X in this case. So it really is a sort of, but it doesn't have to be precisely the same size. That's the little point that I wanted to emphasize. So actually, so the next case to consider, the next thing, if you're an additive combinatorialist, the next thing you think about is, well, we've done C equals 1, we've done C equals 99%. What about C equals 1%? We often talk about things in this way. There are a lot of results in additive combinatorics, which, if I had a longer time, I would go into in more detail, where if you reduce, you've got some local structure that in some algebraic structure happens 100% of the time. If you reduce it to 99%, then things sort of get a little bit perturbed, but you still, basically, it's a robust situation. But if you perturb it down to 1%, then what you can get can be significantly more flexible, but still you have some very clear global structure. So the question was, does that happen in this instance, where you've got just 1% of triples being associative? Of course, 1% means some small percentage, but we like to call it 1%. So what might be a conjecture of what could happen? Well, we could take a leaf out of this book and say, and you can imagine conjecturing slightly stronger things than this, but this is what I'll go for. Actually, let me just give the exact hypotheses I want to consider. So let's suppose X is finite, and I'm going to weaken the hypotheses a little bit. So I'm not going to insist that I've got a binary operation defined absolutely everywhere. I just want it to be densely defined. So I'll have A as a subset of X squared. The density of A is alpha. And we have that phi maps. Oh, wait a minute. Actually, I'm jumping ahead. Perhaps I will make it. I think it is convenient to keep it defined everywhere. So I could just rub out alpha. Then I've got the density as 1. But let's forget A for the time being. It'll come back in a minute. So I'll just go for phi goes from X squared to X. Is 1% associative. So I mean that 1% of all the triples are associative triples. Then there exists a dense subset A. So this is just shorthand for saying if this 1% is a constant C, then the density of A depends only on C and not on anything else. So I have a dense subset of X squared and a map phi from X to some group G such that phi xy equals phi x. Oh, I'm sorry, it is a totally different phi. such that psi xy equals psi x, psi y for all xy in A. Or let's put it a different way. I want to introduce some terminology just to save time when I'm talking. So I'll say that a partial group, and actually I'll generalize this in a moment, but for now, a partial group will be a subset X of a group and then a subset A of X squared. Shouldn't you? Yes. So basically what I want to say is that that we can take the multiplication table of the binary operation phi, restrict it to a dense subset, and then we've got something that's isomorphic to a portion of a group multiplication table. So that would be the... Now, I want to show you an example that suggests that this natural conjecture is actually false. Jason Long and I actually conjectured that this was false. This was a counterexample to the conjecture. And it goes as follows. I take let delta be a maximal delta separated subset of some metric group, and it turns out that a good group to choose for the purpose is but by no means the only one, of SO3. Delta is just some small number, and the smaller you make delta, the bigger the set capital delta will be. And now I want to define a binary operation on delta, so I'll define it as follows. We'll say that phi, I'm going to make it a partially defined operation, but we can make it a total operation quite easily. So actually, that's not, I'll call it circle, so I can write it as infix notation. So let that be by setting x circle y equals z if the distance from xy to z is less than or equal to, say, delta over 20. I've just chosen some arbitrary constant here that's reasonably small. That factor 1 over 20, I mean. So this isn't completely defined because there may not be an element of the delta net that's even delta over 20 far away, as opposed to delta far away. So this maximal delta separated subset, as you all know, will be a delta net. So everything will be within, by maximality, within delta of something. But it won't necessarily be within delta over 20 of something. But it's possible to show, not completely trivial, but it's possible to show that however you choose delta, this operation will, in fact, be defined a positive proportion of the time. It sort of behaves somewhat randomly, and so you would expect a ball of radius delta over 20 to have volume. The dimension of SO3 is 3, so it would have dimension proportional to delta cubed. So we would get this operation being defined something like 1 over 20 cubed of the time, roughly. And more than that, actually, but one can show that, well, let me just we can show that it's got lots of associative triples. So I'm going to show you that subject to something that's not completely, again, not completely trivial to prove, but it is true. So supposing we knew that we've got a triple xyz in delta cubed, supposing we know that all of x circle y circle z, x circle y circle z, and x circle y circle z. So if those are all defined. So that's the non-trivial part. Is that really going to happen all that often, that they're all defined? It turns out that it does happen a positive proportion of the time. But let me now convince you that this gives us an associative triple. In other words, this must equal this. I'll just write a sort of twiddle sign to mean is close to, but where is close to means is within delta over 20 of. So we get that x circle y circle z is close to x times y circle z, because that's true by the definition of the binary operation, which is in turn close to x, y, z equals x, y, z is close to x circle y, z is close to x circle y circle z. And I made 4 approximations along there, so that tells us that this is within delta over 5 of this, but because it's a delta net, because it's a delta separated subset, that implies that they're equal. That's on the assumption that this really was, and all its constituent parts was well defined and therefore an element of delta. So that implies the distance x, y, z, x, y, z is less than or equal to delta over 5 implies now actually this is still the easy part, although even if it's not completely straightforward to get lots of associative triples. A rather harder part is the actual conjecture we made, which was that it is not possible to find a dense subset of delta squared that's isomorphic to part of a, or such that the binary operation restricted to that dense subset is isomorphic to part of a group multiplication table. But that conjecture was actually proved after we'd written our paper, so it's no longer a conjecture. So that's a result of Ben Green, a very nice recent result, which he was going to tell you about this afternoon. I don't know whether he's going to do so remotely. He's not. Okay, so unfortunately, you aren't going to hear about that after all, but at least that means I'm not spoiling his talk by telling you that, although it's in the abstract. So, so it is not possible to restrict restrict the binary operation to a dense subset of delta squared to obtain something, sorry, it's a rather vague word, isomorphic to part of a group multiplication table. So this natural conjecture is not true, but it suggests immediately something that might be true, because this is a very particular sort of example where you have a metric group, and instead of having an exact, you have some subset of it, and instead of taking exact multiplication, you take some sort of approximate multiplication. So what would be a natural, let's go over here, a natural replacement for the conjecture? Modified conjecture under the same hypotheses we can find a metric group and I'm actually going to say something slightly more general because this is what we're going to prove. It's a sort of translated version of the conjecture, and so maps phi, psi, omega, so I'll call that G, from X to G, such that and a dense subset A of G squared such that the images phi x, psi x, and omega x are one separated. This one is not too important. I've got a metric on the group. I can rescale it if I've got something else that's not one, so it's just convenient to make it one. And for every x, y in A, we get that phi x times psi y is close to omega of x operation y. Yes, did I? Yes, it is. So what that's saying is that we can find, instead of finding part of a group multiplication table that's exactly isomorphic to this operation, we can find something that's, or it's better to say it the other way around, we can sort of embed approximately isomorphically into a metric group multiplication table. So we want this delta, oh sorry, less than or equal to, maybe I better not say delta because I used delta over there, it would be slightly confusing. So I'll call it eta. So we want some nice small eta. So that's exactly the situation. So this is what we would have if, in this case of a delta net, we embed the delta net into SO3 using a sort of formal, or using an inclusion map, and we have exactly this situation. We don't have that the multiplication is exactly what we want it to be, but we do have that it's approximately what we want it to be. And so this is not a conjecture either, because this is basically the main theorem that we proved. Although when I say basically, there hangs a slight tail. So we proved something a bit stronger, which I now want to explain. And I want to explain why it was more convenient to prove the stronger thing than the statement that I've written just there. So to do that, I have to introduce. By the way, I have to warn you also, I'm not going to be able to say very much about our proof because it's quite long and complicated and fiddly details and so on. So what I'm going to try to do is restrict my ambition to just trying to get far enough that you can see where the metric group comes from. And then I'll ask you to take something big on trust, but if you take that on trust, which is actually getting to be quite a big if I get that far even. So, so I want to talk about something called the quadrangle condition. So first of all, let's just think, how do we draw these binary operations? What we can do is just draw their multiplication table. So what do we do if we do that? We have a Latin square, i.e. we have an n by n grid with n different symbols, and each symbol appears at most once in each row and column. But we're going to talk about partial Latin squares because we're interested in dense subsets in a moment. But I want to just mention a quite simple result, which answers the following question. Supposing you're given a Latin square and you want to tell whether it's a group multiplication table, how can you do so? So I'm not asking for the best algorithm or anything like that, but just what's the sort of criterion for it to be a group multiplication table? And here is a criterion. You can check easily that if you've ever got a rectangle that looks like that, and because x1, y1 equals a, and x2, y1 equals b, and so on, you find that a, b to the minus 1, c, d to the minus 1 has to be the identity, if I've got my thing correct. Something very similar to that anyway. So 3 of these things determine the fourth. So if I've now got, so to put it a different way, if I've got sort of a, b, c, d dash somewhere else in the group multiplication table, I know that d must equal d dashed. And that's called the quadrangle condition. So the sort of rectangle completion operation is well defined. Once I've got 3 things, I've got a well-defined fourth. And the converse is true. So if you've got a Latin square which satisfies the quadrangle condition, then it must be a group multiplication table. I think in the interest of time, I was going to prove that, but I'll just give a very, very lightning sketch of what you do. So there's one sort of daft trick, which is that you just arbitrarily pick a row and column, and then you declare that that element there is the identity. And once you've done that, you sort of say, I've got an A and I've got a B, and you draw it all in, and you find that what you need for A, B, C to equal A, B times C, just it spits out a pair of rectangles there, and there's the condition that this D must equal this D dash is precisely giving you that A, B, C equals A, B, C. So maybe you'll believe that exercise. So the quadrangle condition implies that you've got a group. Now that's not true anymore if you don't have a full Latin square, but just a partial Latin square. So by a partial Latin square, I mean typically a dense subset of the grid, such that you don't get any element appearing more than once in any row or column. So it's a sort of, so when I say it doesn't mean you don't necessarily get a group. You don't necessarily get a group. You don't even necessarily get something that will embed into a group. And let me just, actually, I can show you, and I think this is quite instructive. There's a very simple way of seeing that. So, and there are more complicated ways of seeing it that are instructive as well, but those I will spare you. So let's suppose I've got what I call a sixth cycle, because if you look at the row-column bipartite graph, that's exactly what it is. Right? So I join a row to a column if there's something in that row and that column. Now suppose I've also got A, B, C, D, E, F dashed. Then exactly the same argument that tells me that D must equal D dash in a group multiplication table tells me that F must equal F dash, because A, B to the minus 1, C, D to the minus 1, E, F to the minus 1 must be the identity. But if you look here, there's no opportunity to get any quadrangles, apart from degenerate ones. So this trivially satisfies the quadrangle condition, but it doesn't satisfy this sort of slightly higher order quadrangle condition, or the sort of 6 cycle condition. And of course you can go up to an 8 cycle, 10 cycle, and not even just cycles. That's just a sort of cautionary thing to bear in mind. But let me just say why that we wanted to focus on quadrangles. It's because very simple Cauchy-Schwarz arguments tell you that if you've got any dense subset of or any partial Latin square, you're going to be able to find lots and lots of these gadgets. So I call this a pair of rectangles where 3 of the labels on the rectangle are the same, and the 4th one might or might not be the same. You just use Cauchy-Schwarz a couple of times, and so you get lots of rectangles, and then you get, by Cauchy-Schwarz, lots of their, you get roughly order n to the 4 different rectangles, only 3 ways of, n cubed ways of labeling, so you must get, by Cauchy-Schwarz, order n to the 5 of these things. So a natural condition to think about, replacing, if you come in from this direction, is to say the maximum number of these that you can have is n to the 5 if x has size n. Again, I can say why that is again. You get n to the 4 possible rectangles because you choose each, including degenerate ones. So you get 2 choices for columns, or n squared choices and n squared choices for the rows. Then, if I want to get another one, once I've chosen A, there's only one B in that row, so B is determined, and there's only one C in that column at most, so that's determined. And then once I've chosen those 3, that's determined regardless of its label. So that gives me n to the 5 of these things. And the quadrangle condition will say that I've actually all of them satisfy that D equals D dashed. And a sort of 1% quadrangle condition would say, what if we know that 1% of the time, when you've got one of these, it actually is the case that D equals D dashed. Now why, so I'll call that the 1% quadrangle condition. Now why is that a better thing, or more convenient thing to think about than the partial associativity condition? It's because we have these Cauchy-Schwarz arguments that guarantee us a big supply of these things. Whereas if you want to guarantee a large supply of, well, there are all sorts of problems. Like if I take a dense subset of the cyclic group, and I just take everything that belongs in some interval. I may well find I've got x times y defined a lot of the time, but I never have x times y times z defined. Things like that can happen. Even if you shift your origin and so on, you find yourself with really difficult problems about hypergraphs that are unsolved and things like that. So finding a good supply of associative triples is difficult. Finding a good supply of almost things that satisfy the quadrangle condition is not difficult. So the actual thing we prove is if sort of a proportion, or if for a proportion C of, I'll call it gamma because I've got some C's there, of the configurations A, B, C, D, A, B, C, D dash. By the way, let me just draw this in a different way, just to emphasize something. So A, all right, B, A, C, D dash. It doesn't have to be sort of in the same order, or it doesn't have to be the same size or anything like that. I just care whether you're in the same row, or in the same column, or have the same label. So if for proportion gamma of those we have D equals D dashed, then we have the conclusion over there. So the conclusion is that we can embed. And now it makes more sense not to say that we have a single set X, but to say that we have a set X and Y. So we have a subset of A is now a subset of X cross Y, and X cross Y is labeled with elements of Z. And all of X, Y, and Z have about the same size. So this is the sort of situation you'd be in if, instead of taking some part of the group multiplication table around the identity, you took something, you translated that portion of the grid somewhere else. We have three different sets instead. But they're closely related to each other. Okay. So maybe I will tell you something that is weaker than what we prove, because this is in itself, I think, quite a nice statement, quite a nice clean statement. So what's the game? We're trying to pass to a dense subset of the set A on which this so A is the set of points in X cross Y where there is a label at all in the partial Latin square. We want to find a dense subset of that A that's very algebraic, that looks like sort of perturbed group multiplication. And so something we might like to do is a sort of potential halfway house towards that, which is to say, well, can we at least pass to a dense subset of A that satisfies not just the 1% quadrangle condition, but the 100% quadrangle condition? So that is a theorem that we prove. We can find a dense subset A dashed of A such that the quadrangle condition holds everywhere. So what that means is that if I ever find this configuration inside A dashed, then I really do have that D equals D dashed. So that's not a trivial thing to prove. What we do it in various stages, but one of the first stages is to get to a subset A dash with a slightly weaker condition, which is not that the quadrangle condition holds everywhere, but if you remember, I used the word well-defined earlier on to say we have a sort of ternary operation that takes three labels of a rectangle and spits out the fourth one. That's well-defined in a group multiplication table. But we could ask for something weaker. We could ask for it to be C well-defined, meaning capital C well-defined, meaning that for each A, B, and C, there are only capital C different possibilities for what the fourth label can be. So that's just one of the steps on the way to getting this, was to get, first of all, get it with some bounded C, and then apply some other arguments to get the C down to 1. But that's a bit unfortunate. I can't go into very much. Why is this not done? We were looking for the quadrangle condition. It's because of what I said before. The quadrangle condition for a partial Latin square does not guarantee that you can map into a group. Or even approximately into a group multiplication table. So what we're going to need is something like this theorem, but for more complicated configurations like the pairs of 6 cycle that I showed you earlier on. So what I want to do next is just tell you what the set of configurations is for which, so basically what we do is we generalize this theorem to an appropriate set of configurations, and then say that if we can get a theorem like this for all configurations up to a certain size, then we can get a metric group out of it. So first I'll tell you what those configurations are, then I'll give some idea of where the metric group comes in. So in order to do that, I need to show you 2 different ways of thinking about. So far everything I've done has been about partial Latin squares, but there's a one-to-one correspondence between partial Latin squares, or there's a correspondence perhaps between partial Latin squares and linear hypergraphs, linear 3 uniform hypergraphs. So I bet I might need to remind the more group theoretic people here what that means. So a 3 uniform, so a graph is just a bunch of pairs of elements of a set. A 3 uniform hypergraph is a bunch of triples. And I like to think of them as faces or triangular faces instead of, so that's what I'll call that a face of a 3 uniform hypergraph. We call it linear if no 2 faces, no 2 distinct faces share an edge. So a linear hypergraph looks something like this. And turns out there are all sorts of very fascinating questions about linear hypergraphs and applications of those questions to additive combinatorics and number theoretic questions and so on. I won't go into all that except just to say that we keep running up against some of those things. We've bumped up against them quite a lot during this work. Now how does that correspond to a Latin square? Very simple. If I've got a set X, a set Y, and I've got a bunch of elements of Z that I'm using to label X cross Y, then for each triple X, Y, Z such that Z appears in position X, Y, I'll take a face of a 3 uniform hypergraph, which will actually be a tripartite 3 uniform hypergraph because I've got 3 sets X, Y, and capital Z, and each face has a vertex in X, a vertex in Y, and a vertex in Z. So I love tripartite linear hypergraphs as well. In fact, all the ones I find most interesting are tripartite, but that's another matter. So why is it linear? That's just because if I know X, Y, there's only one label in position X, Y. If I know X and Z, Z only appears once in column X, so I know what Y is, and similarly with Y. So any 2 of those determine which edge you are, so it's linear. Now, in order to get a feel for this, let's just think about what this configuration here that we talked about before looks like if we think about it as a hypergraph. So maybe I'll let you, again, I'll do this quickly because I think you'll believe me when I say that this turns out to be a cycle of that looks like this. So that's just one rectangle. And then that's got 4 labels that match the 4 labels here. So what we get is another cycle, which is sort of connected to this one by what we call the petals, but I won't do that too much. So one way of drawing that is as follows. So I have two of those joined together. Now, if you imagine these long, thin ones sort of pulled back behind these ones to be roughly the same sort of shape, and you bend these back a little bit and so on, you see that what we've actually got here is the triangular faces of a cube octahedron. So take a cube, chop off the corners, and that gives me a cube octahedron, and that's what we have here. Now, what about if I didn't have d equaling d dash, but it was just different? Then we get something. What the effect of that is that, say that was the thing corresponding to the d, and that was the one corresponding to the d dash. They're no longer joined. So that turns it into this. We've sort of broken apart a little portion of the cube octahedron. And this we call a flappy cube octahedron, because it's got a couple of little flaps. That's not rigid anymore in some sense. So in hypergraph terms, we can say, given a suitable, if you're given a linear hypergraph, tripartite with all the vertex sets having roughly the same size, and if it contains quite a lot of cube octahedra, sort of within some constant like 1 over 100 of the trivial maximum number of cube octahedra that you could possibly have, then you can pass to a dense subset of the faces of this thing, such that there are no flappy cube octahedra. You can get rid of flappy cube octahedra and just keep the good ones. And I won't draw this, but the picture with the 2 6 cycles is just like this, except that having a sort of cycle of 4 faces. You have a cycle of 6 faces and then a corresponding matching cycle of 6 faces that is linked to that one, and you get some shape that's a bit less symmetric than a cube octahedron, but still quite nice. Right. Now I said that there were 2 other ways of looking at it, and they're and they're quite. The second way is also quite important, and will link to, particularly to a group theoretic audience. I think you'll prefer it to the hypergraphs. So I want to define something called a spherical hypergraph. And I'll define it as follows. I take some triangulation of the sphere, and I'm going to draw a specific one that relates to the cube octahedron. So let's just take the triangulation that you get, which we can think of as an octahedron. If I flatten out these spherical triangles into actual triangles, I'll get an octahedron here. But similarly, it's a triangulation you get just by taking the 3 coordinate planes, whatever. And I want it to satisfy an additional property which we call kaleidoscopic, which is that there's a 3 coloring of the vertices such that each triangle there's a proper 3 coloring of the vertices. So each triangle has 1 red vertex, 1 blue vertex, and 1 green vertex. If that's the case, then if you've got a vertex here, let's say that's red, then these ones have to alternate between blue and green because it's a proper coloring. Which implies that the number of triangles that meet any vertex has to be even. So we just want that condition for reasons I'll explain later on. But you can forget about it mostly. Now, if I want to turn this into a linear hypergraph, there's a nice easy way of doing that, which is to take each triangle in the triangulation and join the midpoints, so to speak, of its edges. Or more abstractly, I could say this edge is a vertex of the hypergraph or something like that. But and you see that if I do that, I'm precisely going to get the cube octahedron. I'll get 4 triangles going around the top, 4 triangles going around the bottom, and they'll all be linked in an appropriate way. So there's a sort of natural correspondence between suitable triangulations of the sphere and at least certain hypergraphs. And the ones that you can obtain that way we call spherical hypergraphs. So this is a spherical hypergraph, and so is the one that I showed you, so is the one that you get from 2 6 cycles. But you can get more complicated spherical hypergraphs as well. They don't all have to be just pairs of cycles. And so our more general theorem. What's the? I'll just utter the words Van Kampen diagrams to say that I'm going to mention Van Kampen diagrams a bit later on. So surfaces one is familiar with. But I want to talk about that in just a moment. The generalization that we have of this theorem, I haven't said what a flappy spherical hypergraph is. So a flappy spherical hypergraph is do a suitable triangulation of the sphere, fill in these triangles, and then just pull it apart at some point like that to create some flaps. The generalization is we can find a subset A dashed of density at least some gamma that depends on that was the density of A that I started with, maybe beta was the sort of how good a quadrangle condition that you had. Actually, we can forget about alpha. Let's just go for the beta. Alpha would be we satisfied the alpha quadrangle condition. I alpha we get alpha n to the fifth quadrangles. We don't really need to worry about the density of the set A. And also on a positive integer k, such that there are no flappy spherical hypergraphs suitably translated back into some configuration with that inside the labeled grid of size less than or equal to k. So the real take-home point here is quadrangle condition corresponds to a certain hypergraph. We generalize that hypergraph. We get a generalized quadrangle condition up to size k, and we can, for any k, we can eliminate the structures up to size k. But incidentally, an example, you might be thinking, is there an example where you can eliminate them up to size 100 but not up to size 200 or something like that? If you want such an example, you just go back to that SO3 example. You just make your delta small enough, then the proof that I gave of associativity generalizes up to a certain point, and then it breaks down. So that's maybe just worth a quick mention. So now let me just talk about I think I can just go straight to what the metric group is going to be now. So let me just, actually just before I go say what the metric group is, let me just retranslate the notion of a flappy spherical hypergraph back into surface terms. So if we're pulling apart, say, this point here, we can think of it instead as saying that we pull apart that edge into a sort of slit. And if we do that, we now have not a triangulation of the sphere, but a triangulation of the disk. And it's a triangulation which has a boundary that's got just two edges. So we have something like this. And then a sort of, and then some other stuff here, say. Something like that. And if that one's labeled x and that one's labeled, let's say y in that direction, this will be a Van Kampen diagram. Oh, well, no, I've got to explain what where the Van Kampen diagram comes from independently. So what we're going to talk about, the group is going to be the following. It's just going to be remember I've got like 3 sets, x, y, and z. X was a set of columns, y was a set of rows, z was a set of labels. So I'll just take the free group on, so with generators x, y, and z. I'm assuming x and y and z are disjoint, so I'll take disjoint copies if I have to. Let's go for a metric group. So actually it won't be strictly a metric group, so I'm going to allow infinite distances. So I'll say that the distance between one word W1 and another word W2, oh sorry, before I say that I need to say some relations that I'm going to consider, but I'm not going to quotient by these relations. This is a very important point to make. The relations are going to give me a metric, they're not going to give me a quotient. So consider, so given our labeled or partial labeling of x cross y, take or consider all relations x, y equals z such that label z appears in position x, y. So why is this a sensible thing to consider? Just because if you've got, it's sort of answering the question, how do we know if we can embed into a group or into a group multiplication table? Well, if we can embed into a group multiplication table, then we can find some images of these things, and we will have to have that x, y equals z. So it'll have to satisfy those relations. So if we're ever going to be able to embed into a group multiplication table, then we will be able to embed into the group that I'm not about to define, namely the free group on these generators quotiented out by, the group with those generators and these relations. So let's just think about what can go wrong when you try to do that. Right? So why can't you just do that straight away and there's your embedding? And the reason is that it can all sort of collapse. And the way it collapses is that you end up proving that some of these generators are equal. So we can't just take, well, I won't write that down. So we can't just take this group quotiented by those relations and hope for the best, because it could be easily just, it turns out it could be the free group on 2 generators. That's the simplest it could be if everything collapses down. But we're not going to think about it like that. We're going to think about it as sort of how rapidly it collapses, so to speak. So now let's define my metric on the free group. We'll say let the distance from W1 to W2 be the area of the smallest Van Kampen diagram with boundary labeled, I don't know quite, W1, W2 to the minus 1. So I have some word like that. That's W, and that's W1, that's W2. So the boundary here is W1, W2 to the minus 1. And it's triangulated in some sort of way corresponding to these relations that gives us a proof that these two words are equal. So another way of thinking about it is the distance from W1 to W2 is the shortest proof that W1 equals W2 given this set of relations. And so another way of interpreting this combinatorial theorem is to say that we can pass to a subset which may not embed into a group multiplication table, but at least you can't prove easily that it doesn't embed into a group multiplication table. You're going to need a heck of a lot of relations, at least k of them, in order to prove that this leads to a problem and leads to 2 generators being equal. Oh, so what I want to say is, yeah, so what this, the more precise interpretation would be that the shortest proof that 2 generators are equal has length at least k. So sort of say x1, x2 to the minus 1. You can't prove that unless you use at least k relations. Or, going back to the metric, that's saying that the distance between any two generators is at least k. So what we get is that the sort of main theorem implies generators are k separated. By the way, it's easy to see that, or easy to check that the distance between a generator in X and a generator in Y is infinite. You certainly can't prove that those are equal. But so these are generators in the same set, they're k separated, but also we have that, but also we needed our multiplication to be approximately correct when we did the embedding. So what's the embedding going to be? It's just going to map X to the corresponding generator of the free group and so on. So it's the obvious sort of inclusion map. But so we also get that if Z appears in position XY, then, well, we have the following triangle. So it itself, we have a proof of length 1 that xy equals z. So then we get to the distance from xy to z equals 1 in the group G. So we have, so if k is large, then we can rescale and say that the generators are 1 separated and the distance is delta or something, or 1 over k. So this gives us our approximate embedding into a group multiplication table. It might seem a bit sort of strange and abstract, and in a way that's true, because I think there is more work to be done here. So this does prove that you can embed it into a metric group, but there are lots of, it's clear, we haven't really thought about this much, it's clear that there are very strong restrictions on what that metric group can be like. It can't be too high dimensional, for example, because the balls then, their volumes increase too much when you expand them, and things like that. So meaning, sorry, I'm a little bit, so if we multiply everything by, oh, I see what you mean. I thought we'd check that it was invariant on both sides, but I'm not sure I can answer that question in real time. I'll think about that in a minute. So what I was going to say was that what we have here is quite close to the definition of an approximate group, but it's an approximate in two different senses. So we have an approximate group in the sense of, for people who know about approximate groups, in the normal sense of approximate group, but with an additional metric approximation, because the multiplication is only, so we call them rough approximate groups. And it seems likely that there should be some sort of structure of rough approximate groups that is somewhat similar to the structure for approximate groups, but that we've not tried to do. But if one could do that, then this slightly abstract conclusion would then become much more concrete. And I think, I think it's not a coincidence that no, actually, I'm not going to say what I was about to say. But certainly, I will repeat what I said earlier on. You can't just sort of take any old metric group and perturb the multiplication and hope that you get an example here, because you just won't get enough things being defined. So that's a big restriction that we've not fully explored. Maybe one other final remark I'll make is, you might ask, can you do something similar for abelian groups? So is there some small condition like the quadrangle condition that holds in an abelian group, and then if it holds 1% of the time, you can sort of get some approximate abelian group structure? And the answer is yes, and we've got a monster paper, not yet on the archive, but proving that paradoxically, or slightly counterintuitively anyway, that turns out to be significantly harder than the non-abelian case. Roughly speaking, because the surfaces that we consider here have genus 0, and for the abelian case we have to look at surfaces of arbitrary genus. At least they're orientable, but arbitrary genus, and that turns out to create all sorts of extra complexities for reasons I can't go into here. But I've run out of time, so I shall stop. Well, that starts coming in. Well, what's your precise question, actually? So the higher genus comes in when we look at modifying all this to look at abelian groups. And for sort of more technical reasons, as I say, that but
For example, like this condition of like saying that like any input coming from K approximate to the sphere like has to be satisfied for the
oh, I see. So if you say in a torus, I think it's not the case that, I mean, I think you can have flappy toruses, so to speak. You can have sort of suitable triangulations of the torus that give rise to hypergraphs, and then you can so it's been a little while since I thought about that, so I'm sort of 90% confident that what I've just said is the case, that in an arbitrary group multiplication table, it does not follow that there are no sort of flappy toroidal hypergraphs. But in an abelian group, it does. It may not be that you need the full strength of abelianness, but I wish I had an example I could just give straight away. But I no longer have it at my fingertips. Yeah, sorry about that. I may be able to sit down in a quiet corner and come up with an example fairly quickly, but actually, wait a minute. So I think I remember now. It's coming back to me how I came up with an example at some point, which was just I took some just arbitrary-ish group multiplication table and just arbitrarily looked for a torus inside it and checked in a sort of brute force way. Did the things match up, and then they didn't, or something like that. So that's not. So that's partly why I can't now give you the example. I sort of go through that calculation. So let me just tell you what the nice properties of SO3 were. So first of all, we could not do it for an abelian group. In other words, we could prove that in an abelian group, if you've got some approximate thing, you can more or less change it so that the theorem is, yeah. But secondly, you want it not to be too high dimensional. So one of the things we looked at was a Heisenberg group. And we still believe that that also gives a counterexample of a very similar kind, a sort of approximate multiplication in the Heisenberg group. But we were unable to prove that, and we didn't manage to prove it for SO3 either. But it seemed like a more convenient example to look at. Another important aspect of both those groups was that they were low dimensional, so that balls didn't expand too quickly, so that the multiplication had a chance of being defined. It has a reasonably good chance of being defined. And so Ben Green proved it for SO3, and he had a go at the Heisenberg group, and that's still open actually. So if you've got an approximate multiplication on the Heisenberg group defined suitably, can it necessarily be restricted to something that's isomorphic to part of a group multiplication table? It seems that the answer is probably no, but
Do you expect that something like this is true for like any simple group? Or like compact simple?
Well, yes, I mean the statement would be, yeah, I think I probably would expect that, as long as it's not cyclic, or but I would expect that. But the parameters would get worse as the dimension increased and that sort of thing. So for any fixed simple group, if it had a high dimension, then you just get worse numbers coming out. But that's a small detail.
What about the affine group of Brine? Somehow less appealing than the Heisenberg group.
Yeah, we haven't thought about that one at all, but maybe that would be a good one to look at. It would be nice, actually, to have so Ben Green's proof is very nice, but it makes use of the big paper, Breyer, Green, and Tau. So the answer that comes out is not quantitative, so that's one thing that is also open if you want. So can we get a quantitative version of that theorem? So, but in general, could one get a proof that doesn't use quite so much machinery? And maybe if one could identify a suitable simple in the colloquial sense group to look at, that could be nice. Yes, we hadn't thought about that one.